In the first part of the talk, we have discussed new physics searches at the Forward Physics Facility. Experiment at the FPF will also lay out opportunities for interdisciplinary studies at the intersection of high-energy particle physics and astroparticle physics. This is feasible by looking at the large flux of LHC neutrinos, which can be probed in low background environments at a safe distance away from the interaction point. The second part of the talk is mostly based on these three papers down here that you can also consult for further details and references. LHC neutrinos originate in the decay of charged pions, kaons, hyperons, and charmed hadrons, making the measurement of the neutrino flux a unique probe of forward particle production. The feasibility of such LHC neutrino measurement has recently been demonstrated with the phaser prototype, which observed the first neutrino interaction candidates at the LHC. Ultra-high energy cosmic rays supply a particle beam without financial burden to study collisions at center of mass energies and kinematic regimes not accessible at terrestrial colliders. The cosmic ray air showers are driven by hadron-nucleon collisions with low momentum transfer in the non-perturbative regime of QCD. The shower description is therefore based on phenomenological models which are inherently uncertain due to, first, the lack of a fundamental theoretical description of soft hadronic interaction, and second, the large extrapolation required from collider energies to the ultra-high energy cosmic ray range. Along this line, data from the Piaget Observatory suggests that the hadronic component of showers initiated by cosmic rays with energy between 10 to the 9.8 and 10 to the 10.2 GeV contains about 30 to 60% more muons than expected from simulations. On the one hand, the discrepancy between simulations and data has also been observed in the telescope array data analysis, and note that both TA and Auger have an exposure to the same energy range of cosmic rays. On the other hand, the muon deficit of simulated event is not observed in iSTOP data. However, the center of mass energy per nucleon pair of these iSTOP showers is well below those of LHC collisions. So these showers are not so relevant for the discussion we are having here now. Today, the best hope for resolving the muon mismatch involves decreasing the energy fraction lost to photon production in the description of hadronic collisions, because this is the only known modification of the cascade development which increases the mean muon number without encountering any restriction from other shower observables. The required suppression of the pion production could come from an enhancement of strangeness production. Now, a gauge for an enhancement of forward strangeness production is the pion-kaon swapping probability that we will apply here to the event generator CB. So let me then define the pion-kaon swapping probability as a function of pseudo-rapidity eta. Fs, of course, varies between 0 and 1, measuring of the swapping probability. And we are going to set in our simulation a threshold on pseudo-rapidity of 4. Okay, so we will change pions for kaons with pseudo-rapidity larger than 4. And so we will do a simulation with IRES and Sibyl using the ultra-high energy cosmic ray nuclear composition reported by the Piaget collaboration. And we do the simulations, and we compute the dimensionless muon number as a function of energy. And the dimensionless muon number is defined as the total number of muons at ground divided by the average muon number in simulated proton showers at 10 to the 10 GeV and 67 degrees. Here we have Auger data, and the dotted line here indicates the result from the simulations. taking Fs equal to 0, meaning no swapping between pions and kaons. And of course, we cannot reproduce the data, as we said. So as we start increasing the value of Fs, we are approaching the region of the data. And if we assume that the only effect that is the only mechanism or effect that should originate the mismatch between data and simulation is this strangeness enhancement, then we will require a swapping probability equal to 0.4. But of course, there should be more than one effect. There should be, for instance, nuclear effects that are also playing around there. But let's take for the moment that this is the only effect. And this is interesting because this effect is the effect that the forward physics facility can probe. And so we will see how much or what's the power to distinguish between these different values of Fs. The amount of forward strangeness production is traced by the ratio of charged kaons to pions, for which the ratio of the electron and muon neutrino fluxes is a proxy that will be measured at the FPF. Pions primarily decay into muon neutrinos, but kaon decay leads to fluxes of electron and muon neutrinos. Moreover, muon and electron neutrinos with different parent mesons populate different energy regions. And so the spectral shape can be used to disentangle the neutrino origin. This is very well visible in the figure, where we plot the number of interacting neutrinos at the flare detector of the FPF as a function of the neutrino energy. On the left, we have electron neutrinos. On the right, we have muon neutrinos. We can see that the different colors indicate different parent particles. Pions is plotted in red, and in blue are plotted the kaons. So we can see that the electron neutrinos coming from kaons peak at a different energy from the electron neutrinos, from the muon neutrinos coming from kaons. Okay. And the muon neutrinos coming from pions, again, peak also at a different energy range. So what is the idea here? Well, the solid line indicates no swapping probability, Fs equal to 0. And the other dotted and dashed lines indicate an increase in Fs here, 0.1, 0.2, and 0.5 fiducial values taken. And of course, for pions is the opposite, the solid line, and then the other ones, the number of pions should decrease. Okay, but it is interesting that there is a significant difference at the peak between 0 and 0.1 already. There is a large difference between 0 and 0.1. And I think this is a remarkable result. For an Fs equal to 0.1 or 0.2, the predicted electron neutrino flux at the peak is 1.6 and 2.2 times larger. Okay, so when compared with Fs equals 0, no? So 0.1 is 1.6 larger than Fs equals 0, and Fs 0.2 is 2.2 larger than Fs equals 0. And what is interesting is that these differences are significantly larger than the anticipated statistical uncertainties at the FPF. So this means that the FPF will be able to provide a measurement of the pion to kaon ratio, okay? A direct measurement of the pion to kaon ratio. Furthermore, there is almost no variation in the neutrino flux by changing eta 0 from 4 to 6, okay? So if we change the threshold from 4 to 6, you can see that there are no changes in the flux. Then we have here, sorry, eta 0 equal 8. So if we demand eta 0 to be equal 8, so this affects the low energy part of the neutrino spectrum. Okay. And at the peak, there is almost again no change. Altogether, we can conclude that phasor nu and the FPF neutrino flux measurement will provide invaluable information to measure the rate of forward strangeness production through a direct measurement of the pion to kaon ratio. Okay? This measurement then could become a unique asset in addressing the ultra-high energy cosmic ray muon conundrum. Now, another aspect of high energy astroparticle physics that I would like to discuss concerns ice cube neutrinos. Okay? So there is absolutely no doubt that IceCube has discovered a cosmic neutrino flux. However, the shape of the spectrum and the sources where these neutrinos originate are still a matter of debate. Okay, there is no consensus reached on that part. In particular, we need more data, and that will come both from IceCube and IceCube Shen 2. But here we have the 6-year data sample on the top and the 7.5-year data sample on the bottom. And we can see that the 6-year data sample can be fitted with a single power law with a cutoff and a broken power law. The motivation for the broken power law in the 7.5-year data seems to disappear because we are filling in this energy being here that was empty. Okay, so it's more likely that we have a single power law. And there is a big difference between having a single power law that we extrapolate to high energies. No, we feed this data and extrapolate to high energies, that having a single power law with a cutoff. And in particular, there is here some problems with the 90 CL limits for the extrapolation of the single power law. So remember these two curves then, single power law and single power law with a cutoff. The background for these guys, the background for the cosmic neutrino flux is the atmospheric neutrino flux. Okay, so the neutrino flux arising from pion and kaon decays is reasonably well understood, with an uncertainty between 10 and 20%. However, these guys here, the prompt neutrino flux, it's having some uncertainties. This is due to the large uncertainties in the QCD modeling of heavy meson production. Okay. Again, we need information from FPF to try to reduce, if possible, the uncertainties in the prompt neutrino flux. As I said, the cosmic neutrino flux is also subject to uncertainties, and you will see now why I was pointing the difference between a power law without cutoff that gives me this flux and a power law with cutoff. So there is a big difference, because in the second case, when we add the cutoff in the likelihood function, and remember that this one is the one that better fits the region where we have the 90 CL limit. So when we add this cutoff at 10 to the 7.3 GeV, then the prompt neutrino flux becomes a serious background of the cosmic neutrino flux. Okay. So if this were the case, not so much of a problem, but if we have the cutoff in the likelihood function, that is, repeat, the one that better fits the data, we have a problem starting at 10 to the 7.3 GeV. Moreover, there is another point that is interesting to highlight here. A major feature of the high energy end of the cosmic ray spectrum is the increasing fraction of heavy nuclei with respect to light nuclei. So at the end of the spectrum, now it's coming out that we have medium mass and heavy nuclei. And so because of this, we would expect a suppression of the cosmogenic neutrino flux. These flux are produced when these cosmic rays come on the way to Earth and interact with the cosmic microwave background. These are what we call the GCK interactions, GCK collisions. So we would expect that flux, that it's nearly guaranteed because we have the guys coming in, it's going to be reduced. And it may be reduced to this point down here, which suggests that it's below the level of the prompt atmospheric neutrinos. Okay, so if this were the case, then we may be witnessing the end of the cosmic neutrino spectrum in IceCube data. Okay, would that be the case? Well, no matter what, it seems critical to obtain a robust measurement of the atmospheric charm production. Okay, so let's see now what the FPF can tell us about that. So I have here some simulations, also done with Sibyl, showing the fraction of the primary cosmic ray as a function of the cosmic ray energy per nucleon. So we are interested, so this is shown for different particles, muon neutrinos, and electron neutrinos, plotted in solid dash and dotted line, and different energies. We are interested in 10 PeV, which is equivalent to 10 to the 7 GeV. Remember that at 10 to the 7.3 is where the prompt atmospheric neutrino flux could have some, could become the background or could be a noise for the cosmic neutrino. So let's look at this 10 PeV curve here. And so we can see that there is a difference of 30 between the energy of the neutrino at the peak of the distribution. There is a difference of 30 between the energy of the neutrino and the energy of the primary nucleon, okay, the nucleon that created that neutrino. And so because there is a three-body decay in the dominant production of this atmospheric charm neutrinos is via three-body decay, there is a difference between the energy of the charm hadron and the neutrino of a factor of 3. We consider the three-guy massless, so a different factor of 3 between the energy of the charm hadron and the neutrino. And we say that there is a difference of 30 between the energy of the neutrino and the energy of the parent nucleon. So this means that the longitudinal energy fraction of the produced charm quark is 0.1. Okay, 33 give me the 0.1 on the longitudinal energy fraction of the produced charm quark. Alternatively, we can use the Feynman X variable, okay, taking a transverse mass of 3 GeV, and this is the center of mass energy per nucleon, okay, approximated at twice the energy of the nucleon times the mass of the isoscalar nucleon. And now we can get our formula for rapidity and take the approximation that for the a large rapidity, the hyperbolic sign can be approximated by the exponential. And so we have a function here of all known quantities to determine what will be the rapidity in the energy region of interest. So this means between 10 to the 7 and 10 to the 8. So we plug in the numbers here, and we can see that neutrinos that have an energy between 10 to the 7 and 10 to the 8 GeV spans forward rapidity range between 6.2 and 7.8. And this is the forward rapidity range that the experiments at the forward physics facility will deal with. Okay? So in that sense, FPF is in the right range of rapidity in order to provide us information on the relevant region for the prompt atmospheric neutrino flux. Current experiments at the LHC, like LHCb and LHC forward, they deal with lower rapidities. So FPF will give us it's in the right position to give us the information on the prompt neutrino flux when the prompt neutrino flux can become really an alarming background for the cosmic neutrinos. And now this takes me to the conclusions. I would say that the next breakthrough in particle physics is likely to involve long-lived particles. As we discussed in the first part of the talk, here we have the energy scale interaction strengths. Here we have our favorite intensity frontier that I would say it will flourish during the high luminosity LHC era. And this, the forward physics facility will be a main contributor on these searches. FPF experiment operating at the high luminosity LHC will be sensitive to an unexplored phase space for a broad range of long-lived particles hidden sector physics. And as I discussed in the second part of the talk, the FPF neutrino measurement will improve the modeling of high-energy hadronic interactions and will help to reduce uncertainties in the air shower measurement. And by this, I mean also the production of the prompt neutrino flux. Okay. So the time ahead is looks very promising, and we just have to wait for the data to unveil these uncertainties in astrophysics and see whether we can find signals of dark matter, discover signals of string physics, or just new long-lived particles. Thank you.